So the properties of light, generally there is not too many questions involved in here, but light, among all other energies, is a type of electromagnetic radiation. Electromagnetic radiation that travels at the speed of light in a vacuum. The speed of light is a constant 2.998 times 10 to the 8 meters per second. Now, that's not to say it doesn't slow down when it hits various other media like air, water, crystal. All these things will slow down the speed of light, but this is the max speed it can achieve, which is in a pure vacuum. Now, we describe light with two qualities. V, which are nu, which is our frequency, which is in essentially wavelengths per second. But it's essentially unitless per second. And we can use this and lambda, which is our wavelength, which is usually in terms of meters or centimeters. We're talking our wavelengths of visible light, which we see. It's usually, I think it's between 400 nanometers and maybe like 650 nanometers, something like that. Don't quote me exactly. I don't remember them perfectly. But with the Roy G. Biv. Below the Roy G. Biv, we have infrared, and then radio waves, or infrared, microwaves, and radio and TV waves. Above, we have ultraviolet, we have X-ray, and we have gamma. All of these are examples of electromagnetic radiation. All travel at the speed of light. All can be described the same way. There's two major equations from this chapter, from this little thing, is that because of the measure of wavelengths and frequency, we can say that these are inversely proportional, so that the wavelength times the frequency is equal to the speed of light. So as one goes up, the other must go down. And the other equation is that energy is proportional to the frequency, where energy is equal to h nu. H is Planck's constant, 6.626 times 10 to the negative 34th joule seconds. Okay, so let's go ahead and do at least one quick question. Like if I said we have an energy, some sort of speed of light, we have like some sort of wave ray with, let's say 125 nanometers. And we want to say, what is the frequency or what is the energy? So the one thing you really have to watch out for is units, because speed of light is in meters per second. In order for this to work, we have to be able to cancel meters to get to frequency. So the first step would always be turning nanometers or micrometers into meters. So nano, so milli is 1,000, micro is a million, nano is a billion. So there's 10 to the 9th nanometers in 1 meter, meaning this is going to be 1.25 times 10 to the negative 7th meters. Now, to solve for our frequency, we're going to take 2.998 times 10 to the 8th meters over seconds and divide this by 1.25, 10 to the negative 7th meters. What that's going to give us is units of seconds. The hardest part here is making absolutely sure that you're dividing by 10 to the negative 7th and not multiplying by 10 to the negative 7th, or you're going to get a number that's 10 to the 14th off. 998 divided by 1.25. We're going to get a number something like 2.39. We'll say 2.40, rounding up to sig figs, but times 10 to the 8th divided by 10 to the negative 7th is going to be 10 to the 15th. So this should, because I'm divided by 10 to a negative number, this number should be going up. Now, 2.40 times 10 to the 15th. To get the energy, energy is going to be equal to H 6.626 times 10 to the negative 34th joule seconds times 2.40 times 10 to the 15th inverse seconds. Seconds and seconds cancel out. We're going to have joules. Units of joules. 2.40 times 6.626, 1.59, 34, 16, times 10 to the negative 18th joules. Most of these numbers will be incredibly small when it all's said and done. So don't expect a really large energy. We're talking about individual photons of light. If we talked about multiple photons, you would be talking about a very, very big number. But right now we're talking about photons. It's like saying trying to measure the mass of one atom. It's going to be in grams. It's going to be a really small number. But if we talk about a mole of atoms, then suddenly the number gets a whole heck of a lot bigger. So this is like the light produced by the excitation of one electron. We use this to try to understand the excitation in terms of electrons as they get excited up and excited down. But that's how we treat light.